Hello, this is lecture 2 of plastic analysis of structures. So let me begin. Now let us see a few definitions. Now what is working load? It is the maximum load or the highest load which is likely to occur in the service condition throughout the lifetime of a structure. Collapse load or ultimate load, it is the maximum value of load such that the structure fails or it collapses at this value of load. Now let us see what is load factor. This load factor is used in plastic analysis. It is defined as ratio of collapse load to working load. This load factor depends upon various factors such as support conditions, nature of loading, geometric shape of the structural element, workmanship, and quality of material. Now let us see the difference between elastic approach and plastic approach. So in elastic method, material is not totally utilized and therefore it is uneconomical. Whereas in plastic method, material is fully utilized, the design is based on plastic analysis and therefore it results into smaller element size, so it's economical. Now in elastic method, the factor of safety is adopted to cater for any defect in workmanship and material. So factor of safety is given as yield stress sigma y divided by working stress sigma w. Whereas in plastic method, the factor of safety with respect to load, or which is also called as load factor, is adopted to cater for any defect in workmanship as well as material, and the load factor is given as Pu by Pw, that is ultimate load divided by working load. For indeterminate structures, elastic method is lengthy and complicated, whereas for indeterminate structures, plastic method is quick, simple, and is having logical approach. Again, in elastic method, failure load cannot be estimated, whereas in plastic method, failure load can be estimated. Now let us see the ductility of steel. We know this famous curve, that is laboratory stress strain curve for mild steel when tested under tensile condition in universal testing machine. So y-axis is stress and x-axis is strain. Now initially O to A is a linear region, then D to E it is perfect plastic or yielding, then from E onwards up to approximately F or beyond that it is strain hardening, and then it is necking up to failure, that is G. So mild steel is a ductile material. The ductility of steel is a unique property of this material. The concept of ductility of structural steel forms the basis for the plastic theory. The structural steel is capable to withstand large deformations beyond the elastic limit without fracturing. This figure shows the complete stress strain curve of mild steel. It can be seen that stress strain relation is linear in the elastic range, whereas upper yield point C is reached and then stress suddenly comes down to lower yield stress at point D. However, the strain then increases up to point E at constant stress. This represents the plastic range. Beyond E, the strain goes on increasing with further increase of stress, and material is said to be in a state of strain hardening or in a range of strain hardening. Now, the metal of the rolled steel beams, it doesn't usually exhibit any upper yield point, and therefore the theory of plastic bending is based on the assumption of a steel without upper yield point. The strain up to point E in this graph is approximately 1.5%. In plastic design, at the ultimate load, the critical strains will not have exceeded above 1.5% elongation. Hence, the strain hardening range is neglected in simple theory of bending. This reduces the complications in the calculations and still leaves the major portion of reserved ductility of steel, which can be used as an added margin of safety. Now again, let us go to next slide, that is idealized stress strain curve of mild steel. So just now we saw laboratory stress strain curve, but again we use the idealized stress strain curve in plastic analysis, where initial portion is elastic and then again the graph is assumed to be flat, so that is plastic region. So that shows the idealized stress strain curve. Now let us go further. Now let us see a very important concept of plastic analysis, that is plastic bending of beams. Now I have taken on simply supported beam AB such that a point load is applied at C, that is center, and the load is being increased continuously. So how that beam behaves under the increasing load? Let us see. So here there are 5 figures, that is elastic, second is also elastic, third one is elastoplastic, fourth one is elastoplastic, and final one, which is very important, is plastic. Whereas this first figure is nothing but the section of the beam. Now when the bending stresses are within the elastic range, bending stress distribution will be as shown in this figure 1, that is elastic. As the moment is increased, the yield stress will appear in the topmost fiber here as shown in figure 2. It can also appear in the bottommost fiber also, but randomly I have chosen as the topmost fiber. Now what is yield moment My? It is the moment of resistance of section when extreme fiber attains its yield stress first. That means here whenever this extreme fiber it has attained the yield stress first initially, then the corresponding moment of resistance of that section is called as yield moment. Now from strength of materials we know the pure bending equation, that is sigma by y is equal to m by I. Therefore obviously m is equal to sigma into I by y. Therefore my, that is yield moment, is sigma y, that is yield stress, into Ixx, that is moment of inertia about horizontal neutral axis, divided by y max, that is y max is distance of extreme fiber from the neutral axis, and therefore we can write my is equal to sigma y into Ze, where Ze is elastic section modulus. We have learned it in strength of materials, and it is defined as ratio of Ixx by y max. Now with the further increase of bending moment m, the yield will also occur in the bottom fiber, and it will spread inwards in the top portion as shown in figure 3. That means it is elastoplastic. That means as we increase m, the bottom fiber also now it has attained sigma y, and slowly it will start spreading inside. Now the further increase of m will cause the yield to spread further inwards towards the plastic neutral axis, which is shown in figure 4, that is elastoplastic. A stage is ultimately attained when the yield spreads right up to the plastic neutral axis and the section becomes fully plastic as shown in figure 5, that is last figure, where I have written plastic. That means every fiber above the neutral axis as well as below the neutral axis, it has attained the yield stress, and such a stage is called as the plastic stage, where the moment is plastic moment. So here I have written plastic moment MP is the moment of resistance of that beam section when all the fibers have yielded, and obviously this MP is given as sigma y into Zp, where sigma y is as usual, it is a yield stress, whereas Zp is the plastic section modulus. So this is what I wanted to tell. Now further we will continue in lecture 3.